Hi everybody, my name is Omar Guayed. I'm a fourth-year PhD candidate at NYU Tandon School of Engineering. I wanted to talk to you a little bit about how high-powered lasers can affect phase change in supersaturated solutions. I'm going to do this by introducing non-photochemical laser-induced nucleation, laser-induced phase separation, and we're going to study it using a solution of aqueous glycine. Crystallization is a part of our everyday lives. From food to medicine to cosmetics to photovoltaics, it's everywhere around us. So the study of crystallization and nucleation is incredibly important. People want to have high-speed, pure, 3D controlled materials in order to be able to control what the output is or what the functionality is of the material that you're forming using these crystals. On the left here, you can see an example actually that of crystallization that we've all done since elementary school, and that's you make rock candy. You put 2 parts sugar, 1 part water, heat it, let it cool so that way it's super saturated, and then you put a stick inside of it to form the crystals. Crystals are just the stacking of atoms or molecules in a specific way. The different ways that the same molecule or atom can be stacked are called polymorphs. A common polymorphic system that's well known is the carbon system. So you have diamond, graphene, or buckyball. If you want to study how lasers affect supersaturated aqueous solutions, a good system to study would be glycine, a well-known, well-studied system that has 3 polymorphs, alpha, beta, and gamma, that you see here in front of you. Recently, it's been reported by Sefcik and al. that glycine actually forms nanodroplets before it crystallizes. If the nanodroplets are too small, they'll redissolve to glycine molecules in clusters, only to reform other nanodroplets. If they're large enough, then they'll actually form a crystal. Without further ado, I'd like to introduce you to NPLIN, or non-photochemical laser-induced nucleation, a technique of crystallization discovered by Dr. Garrett and al., in which you shoot a laser into a supersaturated solution to form crystals. Here is a reproduction of the initial experiment of urea and water. Essentially, if you shoot a high enough powered laser in a high enough supersaturated solution of a material that's susceptible to NPLIN, you'll get crystals in the beam path. Not only can you make crystals in high speeds, you also can control your crystals. So one example is you can change your optical setup, allowing for linearly polarized light or circularly polarized light to hit the same supersaturated solution and get a higher probability of gamma glycine versus alpha glycine. You also have 3D spatial control. There you can see in an agarose gel a KCl water solution in which someone wrote out laser just by changing where the beam is pointing. Similarly, we were able to crystallize stellar dendrites in a glycine water solution inside of an agarose gel. But if you leave it alone, you get this tree branch structure that you see on the left. There are 3 possible mechanisms for NPLIN. Optical-Kerr effect, the first reported and most controversial, is the idea that the molecules are aligning themselves with their most polarizable axis parallel to the direction of the applied electric field. This was reported by Dr. Garrett. Similarly, Dr. Alexander and al. Reported that it's probable the laser itself is adding energy into the system so that subcritical clusters can become supercritical clusters and nucleate. Finally, Dr. Nod and al. Reported that laser heating of impurity nanoparticles, or basically that no matter how pure your solution is, there will always be impurities that will be superheated by the laser, thereby causing for nanobubbles, and these nanobubbles act as heterogeneous nucleation sites. There are many different types of NPLIN methods. I'm going to introduce you to 2 separate types. The first I've already introduced you to, unfocused intense nanosecond pulse method, in which you shoot an unfocused nanosecond pulse beam through a supersaturated solution and you get crystals. Here you can see Dr. Alexander and al. Shooting a supersaturated solution of KCl in water, getting a crystal. Another method, the focused continuous wave beam, or essentially where you focus an optical tweezer on the air solution interface. Dr. Sugiyama Masuhara were able to discover this. And here you can see an example of a video that I took of me crystallizing or reproducing this method in a glycine D2O solution. However, if instead of focusing at the air solution interface, you focus at the glass solution interface, you end up getting a dense liquid droplet or a liquid-liquid phase separation. We like to call it laser induced phase separation. Basically, it's a droplet within a droplet. This droplet grows beyond the focal point of the beam, is estimated to have a supersaturation level of 260%. And it's also estimated to stick around after the CW laser gets turned off before it redissolves into the solution. The idea was that glycine clusters are attracted to the focal point of the beam, and due to localized heating, water, along with the smaller particles that aren't large enough to be attracted to optical tweezers, get expelled out, creating somewhat of a thermocapillary effect due to the interaction of surface tension and localized heating along with the optical tweezers. Needless to say, we wanted to study this droplet. So, we chose a supersaturation of glycine that is below the threshold for nucleation in NPLIN systems. Then, we focused the beam at the glass solution interface to form the laser-induced phase separated droplet, and then we monitored it for 100 minutes. Then we did the exact same thing, and then shot it with a intense pulse beam, a single pulse of an intense pulse beam, and then we watched it for 100 minutes. The idea was, if we are able to nucleate this laser-induced phase separated droplet, then using NPLIN, then there might be localized supersaturation increase, or it might tell us a little something about NPLIN that we didn't know before. Here you can see the results of our experiment. In the top video, the LIPS droplet was left alone. You don't see any nucleation except spontaneous nucleation after around 30 minutes, and that's interesting. But also, you see immediate nucleation, almost immediate nucleation, inside of the NPLIN LIPS droplet below. Interestingly enough, all the crystals formed inside the LIPS droplet are alpha glycine, while the crystals that are formed outside the periphery of the LIPS droplet are alpha gamma mixtures, alpha pure, or gamma pure crystals. That's why we studied it further. We did so by comparing it to a 1.5 supersaturated system. That system is within the zone that can be nucleated by NPLIN. So, a higher supersaturated system, when you leave it alone, it doesn't nucleate. While if you shoot it with an NPLIN pulse, it nucleates immediately. Meanwhile, the LIPS droplet takes a few minutes to nucleate when you shoot it with an NPLIN pulse, and it spontaneously nucleates after roughly 40 minutes, 60% of the time. Now that means that there is some sort of residual effect for the LIPS droplet after its formation. Here's what we propose is going on. Inside of a solution, there are nanodroplets, dimers, and monomers. When you turn on the focusing beam, you attract the nanodroplets to the focal point of the beam. Meanwhile, you're expelling the dimers and monomers by having localized heating and expelling the water, and because they're not large enough to be attracted to the focal point of the beam. That is what forms the droplet, the combination of the thermocapillary effect as well as the nanodroplets coming together. Now, after turning off the beam, the thermocapillary effect stops, but the nanodroplets stay together. However, eventually, the droplet loses its formation, but the nanodroplets still stay together, and the monomers and dimers eventually seep in and mix with the nanodroplets. The nanodroplets that are in the center, the dimers are closer to them because they're larger. It is assumed that dimers form alpha glycine while monomers form gamma glycine. This would also explain why NPLIN was stalled, because after you irradiate nanodroplets, there aren't enough dimers or monomers to form the building blocks of a crystal, so they have to take some time to get there. With that, I'd like to thank you for your time and your attention, Dr. Bruce Garretts, my PI, Dr. Janice Aber, who helped train me and set up the experiment, JJ and Tesfea, who are both undergrads in the lab who've helped out tremendously in setting up and continuing the experiment, and my funding agency, NYU Mercec. Thank you and have a great day.